this is going to be the first video in a series of amount of substance ones. So it's going to cover, eventually the whole series will cover various calculations involving moles and concentration. It will cover things like percentage yield, atom economy, and ideal gas equation, and also empirical formulae as well. But I thought the best starting place would be to look at moles, concentrations, and sort of dipping into things like titration calculations, and also calculating masses using various chemical equations. So first thing really, and I found that the problem people tend to have is the idea that they don't know what a mole is, and they find the mole to be this really strange term. But really the easiest way I find to describe what a mole is, it's just a word that describes a number. Just like a dozen is equal to 12, a mole is equal to a different number, and that number is 6.023 times 10 to the 23. So it's slightly larger than 12, and it's really quite incomprehensible how large this is. One way of showing really how big it is that I read that if you were to have a mole of marshmallows, so you have 6.023 times 10 to the 23 marshmallows, they would cover the entire Earth at a depth of about 12 miles. So from that you can see that this number really is quite big. It's a number, the number, but rather the term, the mole, is something that comes up time and time again in chemistry. It comes up within equilibria, obviously balancing equations. It's constantly there. And the reason is it's a lot easier to use the term mole to describe something than to start thinking about individual numbers of atoms, electrons, ions, molecules, whatever it be. It's much easier just to use this term. So when do you normally see the term mole? Well, the classic place for it is within a chemical reaction. So something like A plus B giving us C plus D. Just like algebra, if you had X plus Y, and people can always tell me that X plus Y, how many X do you have and how many Y do you have? I have one X and I have one Y. Well, it's exactly the same with this. I have one A, one B, one C and one D. If I had a 2 here, I would have 2A, 1B, 1C, and 1D. If I had 2 here, I would have 2A, 1B, 1C, 2D. And what I'm talking about when I'm giving those numbers, I'm talking about the moles. So I have 2 moles of A, 1 mole of B, 1 mole of C, and 2 moles of D. Now that's the same even if I look at hydrochloric acid and sodium hydroxide. So this reaction, I can see now that I have 1 mole of hydrochloric acid, 1 mole of sodium hydroxide, 1 mole of sodium chloride, and 1 mole of water. And really what this is telling me is that in terms of the reactants, if I ignore the products for now, because they don't exist until the reaction has taken place. So if I think about 2 reactants, in the case of this example here, 1 mole of hydrochloric acid will react with 1 mole of sodium hydroxide. And in doing so, we would end up with none of this, and we would end up with 1 mole of this and 1 mole of this. So we know that the molar ratio of the reactants is 1 to 1. So 1 mole of hydrochloric acid will react with 1 mole of sodium hydroxide via these imaginary numbers here of 1 and 1. Now if those numbers were actually 0.5, it would react with 0.5 because that sticks to the ratio of 1 to 1. And 0.5 of this reacting with 0.5 of this would produce me 0.5 of this and 0.5 of this. In fact, 0.5 of this reacting with 1 of this would still produce me 0.5 of this, because this is in excess. This is the actual thing that's governing how much of this and this we can make. So in this case, if I had 0.5 of this, it would only react with 0.5 of my 1 available, give me 0.5, 0.5. But that's not something you necessarily have to worry about too much. Now, when we're doing all various calculations that can be associated with this idea of the mole and all the rest of it, there are 2 equations you need to learn. Those 2 equations are these. There's concentration equals moles over volume, and there is also moles equals mass over mR or AR. It depends whether you're looking for the moles of a molecule, mR, moles of atoms, AR. It depends what you use, but essentially you're going to be using relative atomic masses of some sort, either added together or just on their own. This is perhaps the most difficult one of the 2 to use. Neither are difficult, but this is the more tricky one. The reason being that we have a unit of volume that's a bit different really, and that unit is decimeters cubed, and that really stems because actually concentration is measured in moles per decimeters cubed. So this guy over here, this is my mole. So mole per decimeter cubed, mole divided by decimeter cubed, and that's where we get this unit from, mole divided by decimeter cubed. The other way, you can write this as mole slash dm cubed. You can write it as a capital M, molarity, or you can write it as mole dm cubed. In terms of exams, you're going to see it written as either that or as that. Probably less so this, maybe in older questions, but still it means the same thing. The one thing here is converting volumes. If you're dealing with a question and you're going to have to calculate concentration, you know moles and you know volume, or calculating moles from a known concentration, known volume, you're 99% of the time going to be using, if not more than that, going to be given the volumes in centimetres cubed. That's not going to help you, because if you put centimetres cubed into here, you're going to get the wrong answer. So you've got to convert it, and you convert your centimetres cubed into decimeters cubed just by dividing by 1,000. And I always say this to the kids I teach: whenever you are dealing with a volume and you're looking at calculating concentrations, whenever you use that volume, always divide it by 1,000. So 50 centimeters cubed equals 50 divided by 1,000 decimeters cubed. Easy. On the other hand here, moles mass over mR, we have mass in grams, and we have moles again just in moles. And this mR is a funny one, that it's just really, they're relative terms, so they don't have a unit attached to them. At this point I would actually like to make a point which would have probably been more useful earlier on, but there we go. Although you can actually calculate it now using this, and that is that 1 mole of, which we got an atom, equals its AR. 1 mole of a molecule equals its MR. Actually change that, AR in grams, MR in grams. For example, what I mean by that is 1 mole of, what should we go for? 1 mole of carbon. So 1 mole of carbon. Now carbon is this guy here, we're dealing with carbon 12. Therefore 1 mole of carbon equals 12 grams. Other way around, we'll look at a molecule now. We'll look at carbon dioxide. So 1 mole of CO2, CO2 being 12 add 16 add 16, or 12 add 16 times 2, giving me 44, therefore 44 grams. Just a point to make. Right, the way I'm going to structure this is I'm going to do 3 questions which I've taken from exam papers, and those questions should give you a fairly good idea of how to calculate various moles, masses and concentrations, and I'll work through those one by one. So this is the first one. Okay, question number 1. A student finds that it takes 32.10 centimeters cubed of hydrochloric acid with a concentration of 0.150 mole per decimeter cubed to completely react with 25 centimeters cubed of sodium hydroxide solution. Calculate the concentration of the sodium hydroxide solution, and then you're given a lovely little reaction between hydrochloric acid and sodium hydroxide. Now I'm not going to go into the details of titrations here, because quite frankly I don't really want to at this point, and it's not really needed for this question. There's a bit of basic understanding is needed, and that's really that what we're doing here is we are reacting 2 things, the 2 things being hydrochloric acid and sodium hydroxide, and we are given information for both of them. Now actually, in these questions, you can often ignore, certainly in this one I can ignore this half. It makes no difference to me. I can ignore that, and I can just looking at these 2, and I'm going to link into some ideas that I actually touched on earlier on. So the actual question itself, there's lots of words, the actual question is basically this: calculate the concentration of the sodium hydroxide solution, this guy right here. And the rest of the question is information, lots of words. They use a lot of words in these kind of questions, but if you can basically pull them together and work out what information is being given about what chemical, you'll be fine. So what I would do is I'd get yourself a highlighter and I would highlight in 2 different colours each chemical. So first of all, I know that this is a volume of hydrochloric acid and that this is a concentration of hydrochloric acid. Therefore I know 2 things about my hydrochloric acid. This, on the other hand, it's a little bit messy looking, but there we go. This is a volume for my sodium hydroxide. So I'm given 2 pieces of information about my hydrochloric acid and I'm given 1 piece of information about my sodium hydroxide. Now for this kind of question I'm calculating the concentration, therefore I'm going to need my concentration equals moles over volume equation. Instantly thinking, right, do I remember what my units are? Decimeters cubed, moles, mole per decimeter cubed. And I'm looking to calculate the concentration of sodium hydroxide. So why not just work it out? I'm given a volume, there we go, 25 divided by 1,000, but I don't know my moles. I don't know the moles of sodium hydroxide, so I can't work out my concentration directly. What I need to do is instead, I need to use the hydrochloric acid. And it relies on this idea that hydrochloric acid, from the equation given, hydrochloric acid will react with sodium hydroxide in a 1:1 ratio. 1 mole of this will react with 1 mole of this in a perfect ideal world. And that's what we're assuming here. We're assuming absolute perfect reaction. So 1 mole reacts with 1 mole. If I had 4, it would react with 4. 0.0231 would react with 0.0231. You get the idea. The same numbers, because the ratio is 1:1. Okay, the ratio is 1:2. One of these is going to react with 2 of these. Therefore, you're going to double this number. If the ratio is 2:1. You would halve this to get that. I'm only going to look at this the monoprotic acid, which is the example that will often give you the ratio of just 1:1. You may see a ratio of 1:2 or 2:1, but you just deal with it accordingly by changing these bits. And I'll show you the step later on where you would make the calculation. So I cannot work out my concentration directly of my sodium hydroxide, but I know a volume of my hydrochloric acid and I know a concentration of my hydrochloric acid. Therefore I know my volume, I know my concentration. That means I can work out my moles. So my first step, moles of hydrochloric acid. Rearrange my equation, I find that concentration times volume will give me that. And so my first step is going to be concentration 0.150 multiplied by my volume. My volume this time is 32.10 divided by 1,000. Remember, we've got to convert the centimeters cubed into decimeters cubed. We'll bracket that up, and that will give me a number, and that number is 0.004815. Make that clear. You could do this as standard form if you wanted. You could say it's 4.815 times 10 to the minus 3. Doesn't matter. Either one of those is fine. Big tip for you: do not round this. Don't say, all right, 0.005. You round this here, you're going to get the wrong answer. I would leave this answer in its longest form if possible. Write it down to, I remember when I was at school I used to write it down to maybe 7 decimal places after the zeros, and then use as long a value as I can. Final answer you need to use to give it to appropriate precision, often 3 significant figures. Do not round this though. Do not round midway through calculations. It will be the end of you. If you can use the store function on your calculator, then and just Google it if you can't work it out. That's a really good way of storing numbers and working out and keeping accuracy in your calculations. But anyway, I've worked out my moles of hydrochloric acid, and I've worked out that I have, from this value here, 0.004815 reacted perfectly in this case. Now, because the ratio is 1:1, that means that this hydrochloric acid, 0.004815 of this, must have reacted with 0.004815 of this. Therefore, moles, good job there, moles of sodium hydroxide equals 0.00485. I would lay this out similar to this as well. I would make it so painfully clear what you're doing. Do not make it difficult for the person marking to work out what you're doing. If you do, you might just lose your marks. Okay, it needs to be obvious. you'll often get your marks for the right answer, but you make one tiny mistake, as people do all the time. You know, you make a calculator error, but I've got all my working out. They can see exactly what I've done. I would get all the marks for my working. I would just lose the final mark for the question, for the answer, sorry. So my moles of sodium hydroxide in this case then are equal. If we were dealing with a 1 to 2 ratio, this would be doubled to give me this, the thing it was reacting with. In this case, it is not, so I'm not doing that. If this was a 2 to 1 ratio, I would halve this to give me this number. Now, sodium hydroxide moles 0.004815. I know a volume of sodium hydroxide, therefore I know my moles, I know my volume. So, final step now, concentration of sodium hydroxide is equal to moles 0.004815 divided by volume 25 divided by 1000, of course, as always, and that's it. Get your calculator out, work that out, boom, there's your answer. 0.1926. Now three significant figures arise it, and we'll go for 0.193. Remember, units, we're dealing with concentration, therefore it's going to be moles per decimeter cubed. Lovely. Okay, going to look at a similar question, but one that involves a mass, but then follows a very similar path, and that looks something like this. Okay, a bit of a longer question this time. It's split into 3 parts, A, B and C. So basically what we did last time, we kind of covered all 3 of these parts in one. Now they've actually split it into separate ones. So don't just learn as a template, understand what you're doing each time, because they might split it like this. So anyway, we've got ammonium sulfate, and we've got it reacting with sodium hydroxide to form ammonia, sodium sulfate and water as shown in this delightful equation here. A 3.14 gram sample of ammonium sulfate reacted completely, again, so a complete reaction. This time, rather than having 2 volumes, we've got a mass and a volume. So it reacted completely with 39.3 centimeters cubed of a sodium hydroxide solution. Again, here, looking through this, we've got no mention of ammonia, sodium sulfate or water. Therefore, I'm going to get rid of it. Only because I don't want you to look at this and get confused. This is where the money's at right now. So, first step. Calculate the moles of ammonium sulfate in 3.14 grams of ammonium sulfate. Now, what we need to do here is we need to use a different formula. So we've got concentration equals moles over volume as before, but we've now also got moles equals mass over m(r). So we're going to use that this time because we're dealing with the mass now. We can't use the concentration moles volume because that doesn't account for mass. So how many moles do I have in this mass here? So it's a very easy one. It's just moles equals mass over mR. No rearrangement required. So moles, and state what you're doing. This is the moles of ammonium sulfate, and that is equal to my mass, 3.14, divided by my mR. Now my mR here is going to be nitrogen. We'll put this all in brackets, it's probably easier. Nitrogen is going to be 14. We're going to add to that 4 times, oh, terrible, and then we're going to times that by 2. We're going to add to that my sulfur, which is 32.1, and I'm going to add 4 lots of 16, and that's going to come to, I believe that's going to come to 132.1. So we use that number here, 132.1, and that will give us an answer of 0.0237698. Now, for this one here, a little bit different to the last one. I said don't round in the middle of your calculations. However, what you're dealing with here is you've got 3 distinct questions. You're not dealing with just one question. So calculate the amount of moles in blah 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 blah. I would actually now, because this is a distinct question which will carry a mark, I would now actually write this as, and these were actually separate with lines in between each one. I would now round this, and I would round this to 0.0238. which I know goes slightly against what I was saying, but with this one it was just one question, and it was all done as one portion. Here we have 3 separate questions, therefore it's fairly good to actually do that rounding there. So we've got this value here, so we've got 0.0238, and what I'm going to do is each time I'm just going to actually erase all this and just do all my working down here, but put all the necessary values up there. So part B. Now it's asking us to calculate the moles of sodium hydroxide which therefore reacted. Now this is the good one actually. I hadn't realised this was a different ratio, and that now our ratio is 1 to 2. So 1, 2, 2. Now I've worked out how many moles I've got of this. Well, because the ratio is 1 to 2, it will react with twice as many moles of this. Therefore, moles of sodium hydroxide is going to be this answer before, 0.0238, but I'm going to multiply it by 2. And that's going to give my answer now for how many moles of sodium hydroxide have reacted. And that comes to 0.0476. So 0.0476. Okay, as again, I'm now going to go to the final point here of calculate the concentration in part C. Now, for part C, we're going to have to use the other equation, which is concentration, remember, equals moles over volume. But we can do that fairly easily here. We've got our moles, it's 0.0476. 0.0476. I've got a volume because it's here. Sodium hydroxide, this is my volume of it, 39.3. And all I'm going to do, divide that by 1,000 as before. Remember I said anytime you're using this equation, you use a volume, divide it by 1,000 if it's in centimetres cubed, which is going to be 99.9% of the time. Do the calculation, you've got yourself an answer. And that comes to 1.21119. And again here we've got to do a bit of rounding, so we're going to go 3 significant figures. I'm going to call it 1.21 moles per decimeter cubed. And there we go, we have an answer again. And a fairly straightforward one. Using provided you remember the equations, you can remember the conversion factors and all the rest. The rest of it actually isn't too bad. So final question is another one which involves using moles, but in a slightly different way, but again using the ratios involved. So here we go. So here's my question. Zinc chloride can be prepared in the laboratory by the reaction between zinc oxide and hydrochloric acid. The equation of the reaction is as follows. Blah, 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 blah. A 0.0830 mole sample of pure zinc oxide was added to 100 centimeter cubed of 1.2 mole per decimeter cubed hydrochloric acid. Calculate the maximum mass of anhydrous zinc chloride that could be obtained from the products of this reaction. Okay, so in this question here, it comes up at the end of the paper. I think it was question 7 or something like that. So it's towards the end of the paper. And therefore it's a little bit more of a difficult one. You've got to think a little bit more for this one. And the way it works is as follows. We're given a value for the moles of zinc oxide that are taking part in this reaction. And we just know about the hydrochloric acid. We know its concentration and we know its volume. So the first thing we're going to do, we're going to work out the moles of hydrochloric acid. And we're going to do that again using our equation of concentration equals moles over volume, but we're going to rearrange to give us concentration times volume equals moles, and therefore we're going to do a concentration of 1.2 multiplied by volume, which in this case is 100 divided by 1,000, and that's going to give us 0.12 for our value of the number of moles of hydrochloric acid. Now a quick bit of thinking here will kind of explain the next part, and that is that if I had 0.2 moles of this, it would react with 0.6 moles of this. Whereas I have if I had 0.12 moles of this, because the ratio is 1 to 2, it would react with half of this. Therefore it would react with 0.06 moles of this. Whereas I have 0.0830. So I have an excess actually of zinc oxide in this case. I have too much zinc oxide for acid. So the acid, if you like, is the limiting factor. It is limiting how much we can produce of the zinc chloride and of the water. The reason for that being that, as I say, this has the lesser amount because there's 0.12 which would react with 0.06. Therefore, the moles of this that's going to be produced is going to be half of this, because the ratio is 1 to 2 to 1 to 1. So just to recap on that in case that's a bit confusing, I have 0.12 moles of this. I know that it would react with 0.06 moles of my 0.0830, therefore producing 0.06 moles of zinc chloride and also 0.06 moles of water. Doesn't matter, but the fact of the matter is that it's just 0.06 of each. So I would write that within my question. I would say, therefore, moles of zinc chloride equals 0.06. But of course we're trying to calculate this maximum mass, and the key word here is mass, not maximum, it's mass. So mass of zinc chloride is going to be, rearranging this equation, remember moles equals mass over mR, therefore mass equals moles times mR. So I know 0.06 is my moles, my mR is going to be my zinc, and it's a 2 of my chlorines. Now zinc, if you look at our periodic table, zinc is 65.4, and I know that my chlorine is 35.5, but remember I have 2 of those because it's zinc chloride, ZnCl2. So add that up, multiply by 0.06, and you end up with an answer of 8.184. Now in this case, 3 significant figures, I would go for 8.18 grams, and there you have it. So it's been a fairly sort of quick lesson looking at the idea of calculated masses, concentrations, moles, volumes and all the rest of it. But that's really 3 questions there from actual past exam questions, exam papers, to show you the kind of things that you can be asked and the way those questions work. As I said, the next couple of videos will cover things like percentage yield, empirical formulae, and ideal gas. But I hope that's been of some help. If you have any issues, you have any problems, please do let me know.